Edexcel called pure, complex numbers 4, de Moivre's theorem. Finding multiple angle identities using de Moivre's theorem. You're already familiar with identities such as cos squared theta plus sine squared theta equals 1, but hopefully either at the moment or some point in the second year of the course you will come across your compound angle formulae and your double angle formulae. Yeah, these are very important identities which you may have seen already but will be seen in the upper six if not. So now we're going to look at example 1. We are going to write an identity for cos 4 theta and sine 4 theta. Now these could be done just using some trig identities, but it would be very long-winded and very complicated. So there must be a neater, quicker way of doing this. And the trick is, rather than do them one at a time, we do them both together. So we turn this into cos 4 theta plus I sine 4 theta, and the reason we do them both together is I can now rewrite that as cos theta plus I sine theta to the power 4 using kind of de Moivre's theorem in reverse if you like. Now we're about to expand these brackets, so to make life a bit easier for us, an accepted convention that you may find useful is to write this as c plus is to the power 4, where c is cos theta, s is sine theta. So I'm now going to do a full expansion of c plus is to the power 4 using Pascal's triangle. So doing it very carefully, there's a c to the 4, a 4c cubed is, a 6c squared is squared, 4c is cubed, and finally 1 is to the 4. Don't forget things like I squared is minus 1, I cubed is minus I to the 4 is back to being 1, things like that. And tidying all of this up, I'm still going to use the shorthand notation. So we've got c to the 4, 4c cubed si, minus 6 c squared s squared, minus 4cs cubed I plus s to the 4. Now the really clever thing is we know that that's the same as cos 4 theta plus I sine 4 theta because we originally started off using a de Moivre's theorem. Now if we pull out the real part, because all of these steps are identically the same, so if you look at the real part on the left hand side, that's cos 4 theta, and the real part on the right hand side must be a perfect match. I'm starting here, I'm going to go back to the full notation now. Cos to the 4 theta minus 6 cos squared theta sine squared theta plus sine to the 4 theta. So there's my first of my identities. That's the first one done. The beauty of this method, because we introduce cos 4 theta and I sine 4 theta at the beginning, if you now pick out the imaginary part, you don't need to put the i's in here. The imaginary part on the left hand side is sine 4 theta, and that must be exactly the same as the imaginary part on the right hand side. So starting with this term here, we will have 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta, and there is the second of our identities. So the really important bit is to look for both the cos 4 theta and the I sine 4 theta together. Once you've written it as cos 4 theta plus I sine 4 theta, you can use de Moivre's theorem to write it as a power. Writing it as a power allows us to do this binomial expansion, and once we've done the binomial expansion, we can equate the real parts and we can equate the imaginary parts to get the identities. It's also so useful to know for these multiple angle identities that sometimes we almost do kind of a reverse process, and it's really helpful to find things, for example, like cos to the power 6 theta in terms of multiple angles instead of a power, particularly if we are looking to integrate. So if we remember that z is our definition of cos theta plus I sine theta, so that's fundamental to everything really, then z to the n can be written as cos n theta plus I sine n theta, and z to the minus n can be written as cos n theta minus I sine n theta. If you add these equations together, you get this very neat identity for cos n theta. Cos n theta is z to the n plus z to the minus n over 2. If you subtract them, if you do equation 1 take away equation 2, then you can get this nice identity for sine n theta. Be careful with sine n theta. It has a 2i in the denominator and that minus sign in the numerator. But we now have a very neat way of writing cos n thetas and sine n thetas, which we're going to use in the next example. So here we want to turn sine theta cubed into multiple angles. Okay? So the first thing I'm going to do is to write sine theta using this new definition. I can write sine theta as z minus z to the minus 1 over 2i. So in other words, I've let n equal 1. You could carry on working with it in this form, but I think you'll find it a little bit easier if I cross multiply and write it as 2i sine theta is z minus z to the minus 1. I think that's a little bit easier. We're now in a position where we can think about cubing both sides. So if I cube the left hand side, I would get 2i cubed. I'm going to leave it as 2i cubed for the time being. You'll see why later. And sine cubed theta, which is the thing I'm looking for. On the right hand side, I can do this as a binomial expansion. Those of you who think of this as a plus b to the n, you now need to think of a as being z, b is minus z to the minus 1, and n is 3. So very carefully, doing the full expansion, I'd get a z cubed, a 3z squared minus z to the minus 1, a 3z minus z to the minus 1 squared, and a minus z to the minus 1 cubed. If I tidy all this up, I will get z cubed minus 3z plus 3z to minus 1 minus z to minus 3. Looks a bit odd at the moment, but there's a neat thing we can do now. What we do is we pair the outer terms and the inner terms. If when you do your binomial expansion there's an odd term in the middle, that's fine, just leave that one separate. But you pair them up starting at the ends. So I'm now going to write this as z cubed minus z to the minus 3. I'm going to pull out a minus 3 as a common factor, so I get a nice neat form of z minus z to the minus 1. Again, it might look a bit odd, but we know that this is 2i cubed sine cubed theta. There's different ways of setting this out, but I hope it will help if you now think about dividing both sides by 2i. If I divide both sides by 2i, here I'm left with 2i squared. But more interestingly, look at what it starts to happen if I put the 2i back into these brackets. So I've divided that term by 2i, minus 3. I'm now going to divide this term by 2i. 2i squared is minus 4, so I've got minus 4 sine cubed theta. But this bracket here, if you think of n is 3, that bracket is the definition of sine 3 theta. Minus 3 lots of. Think of n as being 1, that bracket is the definition of sine theta, which we saw at the beginning. Yeah, there's our definition of sine theta. Yeah, we're using it again now. There it is. Divide by minus 4, and we've got sine cubed theta is a quarter. I'm going to use the minus sign to swap these terms round. 3 sine theta minus sine 3 theta. Sorry about that little smudge there. There we go. And that is the way you could write sine cubed theta in terms of multiple angles. You could do, it would be very similar if it was cos theta or if the power was bigger than a 3. So the most important step is to set up whether it's cos or sine. If it was cos, by the way, it wouldn't have an I here and it would be a plus sign. But set up a nice simple equation to get you started. Raise both sides to the appropriate power. Do a full binomial expansion and start to pair them, the first with the last, and then and keep working towards the middle until they're paired up. And if I now, if I divide by 2i, if I divide through by 2i, then I can create a sine 3 theta and a sine theta term. And that brings us to the end of de Moivre's theorem.